listen-only mode.
Good morning, everyone, and welcome to the 13th in the LimitState webinar series for 2015. My name is Tom Pritchard, and our other speaker, who I'll be introducing you to shortly, is Professor Matthew Gilbert. Today's webinar is the assessment of concrete bridge decks using LimitState SLAB, and it will introduce you to the technology behind our automated Yieldline analysis software, LimitState SLAB, and it has a particular focus on bridge deck analysis. First section will be delivered by, as I say, Professor Matthew Gilbert, and then I'll take over with some examples demonstrating how the software can be used for a number of different bridge analysis situations. The main section of the webinar will run until just before 10 AM UK time, so about an hour, and will include 5 or 10 minutes at the end for questions, which can be posted at any time in the question functionality that should hopefully be present in the webinar interface that's in front of you. While we try to get around to as many of the questions as we can, sometimes there isn't always time for every single one of them, so apologise in advance if we can't get round to yours. We do, however, follow up on any unanswered questions after the webinar has finished, and you can also get in touch with us at any time via email at info@limitstate.com. So without further delay, our first speaker today is Professor Matthew Gilbert, and I'll now pass you over to him.
Thanks very much, Tom, and thanks very much to everyone for joining us today for the webinar. Okay, so the first slide I want to show gives a nice example of, on the left-hand side, classic yield line mechanisms of the sort that you might see in textbooks. On the right-hand side, we see, in contrast, yield line patterns that might be identified in the case of elements of a bridge deck, and you can see that they're significantly more complex mechanisms and consequently will be quite difficult to identify by hand. And next slide just gives a different view of those same yield line mechanisms. Again, the hand type mechanisms on the left hand side and the significantly more complex mechanisms that might be associated with the bridge deck on the right hand side. And the key thing that we've been able to do is to automate the yield line method in order to be able to quickly and easily identify the yield line mechanism, whatever geometry you're dealing with. Okay, so what I'll do is I'll move on shortly to explaining how we've been able to do that, and then Tom will talk you through the software and how actually in practice you set up and solve problems of the sort that we've just seen. But before we do that, I'll just say a few words about the company LimitState. It's actually a spin-out company from the University of Sheffield. It's been around since 2006 with the main aim of commercializing academic research. So in other words, getting methods developed in the university out there to practicing engineers. Focus has been on developing powerful tools to analyze directly the ultimate limit state. And the way we do that is by using state-of-the-art optimization technology. And technology which isn't or hasn't traditionally been used in the standard offerings in the marketplace, but which have significant benefits. Because we're a company as opposed to a part of the university, we're able to spend time supporting the software, making sure it's easy to use, and also being rigorous in ensuring that the software is properly validated. So to date, we've developed 3 main engineering software applications: LimitState Ring for masonry arch bridge analysis, LimitState Geo for geotechnical analysis, and LimitState SLAB, clearly of interest today, for concrete slab analysis. And one or more of these tools is in use in most of the UK consultants, of key top 10, top 20 UK consultants at least, and in over 30 countries worldwide. And just show you a sample list of clients. So they range from small companies, local authorities, all the way along to much bigger companies such as AECOM, Arup, and contractors such as Balfour Beatty. So a wide range of companies are benefiting from the software. So if we step back a few paces, what's been our motivation, and what's been the motivation of the university research group, which the company is strongly associated with? Well, if we look at the range of analysis tools that are available to practitioners, one thing we can say is that linear elastic finite elements, or finite elements, have made linear elastic analysis very, very easy to do, whatever the geometry. So essentially, a challenge that was set in the middle of the 20th century has been met. The same can't be said for rigid plastic analysis. So for quickly and easily analyzing the ultimate limit state, the collapse state, we don't currently have flexible and mainstream tools. Instead, we're still very often reliant on the hand-type methods which were developed in the mid-20th century. So here we can see a mechanism for a slab, and relative, limited to quite simple geometries and quite simple scenarios. When I say rigid plastic analysis or limit analysis, what do I mean? Well, I mean that whereas with elastic analysis we assume that Hooke's law is valid ad infinitum, here we neglect elastic strains and we are simply interested in the plateau, the collapse state, and we apply that whether it be a solid body or whether it be a structure. Benefits of the method, if we're looking for establishing the margin of safety of a component or structure, are that when we're thinking of design, we can find more economic solutions. When we're thinking of assessment, then we can very often identify significant hidden reserves of strength compared with when we use elastic analysis for the same purpose. Another view of the same thing, what we find if we look at the range of existing tools for collapse analysis, whatever the sector in civil engineering at least, we find they fall into two distinct camps. At one end, we have traditional tools which are based on hand methods, so very simple assumptions often made that underpin hand calculations that may have been embedded in a simple spreadsheet or in a simple standalone software program. The problem with those tools are as soon as you move away from those initial assumptions by changing the geometry, for example, then you end up introducing considerable imprecision, and you end up with lots of uncertainty about whether your solution is valid or not. At the other end of the spectrum, we have what I've called advanced engineering analysis tools based on, for example, nonlinear finite elements. These tools can certainly take account of differences in geometry, differences in material compared with those simple hand-type methods. The downside is, however, that they are generally quite time-consuming to set up and solve a model. You need considerable expertise, and for many of the kind of one-off scenarios that we deal with as civil engineers, they are simply too expensive. Key thing is there's a large gap between these two types of tool, and what we're focusing on doing is bridging that gap or filling that gap with a range of mainstream alternatives based on numerical rigid plastic analysis. And in terms of applications, we could be talking about geotechnical applications, so slope stability, retaining walls, etc. We could be talking about masonry arch bridges, analysing the capacity of those structures, or we could be talking about slab analysis, which is clearly the focus of today's session. Okay, so moving away from the generality to what I'm focusing on the particular application of interest today. Yieldline method has been a very widely talked about, if in recent years less used method for analysing the collapse state of a concrete slab. So the key driving force behind the method was Johansson in the middle of the 20th century, and he basically developed what we now think of as the Yieldline method. In terms of how we actually use it, what it boils down to is choosing a mechanism and then using, for example, the work method to identify the associated margin of safety, so it could be load factor or the amount of pressure that you need to cause collapse, for example. What you need to do, however, is try a range of possible failure mechanisms in order to be sure that you have the a safe estimate of the collapse state, or strictly speaking, that you don't drastically over predict the true load carrying capacity of your slab. If you're doing this on by hand, then clearly there's a limit to the number of mechanisms that you can try out. And in reality, you'll spend a reasonable amount of time if you're doing this by hand, but a finite amount of time. And inevitably, it won't be possible necessarily to find the true critical collapse mechanism. Benefits of the Yieldline method are that it's a relatively simple method. Calculations are generally quite simple as well, and you can estimate the collapse load directly. You don't need to iterate towards the solution by increasing the load. You can just analyze the collapse state directly. Once you've got a reasonable representation of the true collapse mechanism, you find that you'll get a good estimate of the likely load carrying capacity of the slab, generally much less conservative than elastic methods. Downsides are that if you don't find a good representation of the true mechanism, then you will end up with non-conservative solutions. And other drawbacks are that you're only considering flexural failure, so traditional Yieldline method doesn't account for things like punching shear, and it's not concerned also with, for example, serviceability prior to collapse. So you have to use other methods if you want to predict deflections under service loads. So the method was developed in the middle part of the 20th century, proved popular at least with researchers in the 60s and 70s, and there were clear practical applications in the bridge engineering context in the 1990s and early 2000s. Notably, Middleton and colleagues at the University of Cambridge developed what's called the COBRUS program, which basically contained a list of potential Yieldline patterns that could be present in a bridge deck, and actually automated the process of analysing each and every one of those mechanisms. And what they found when they applied it to a range of concrete bridges, in this case on screen we've got a sample of 21 bridges, they found that you could get much less conservative predictions of strength than when elastic methods were used. So what we have here on the current slide is a red bar which shows the elastic capacity and a green bar which shows the plastic capacity, and you can see in the vast majority of cases the green bar is significantly higher than the red bar, and in most cases the required 40-ton capacity was identified when using plastic or Yieldline analysis. So, summarize what I've just said. Many existing concrete slab bridges with inadequate flexural capacity turned out to have the required capacity when the Yieldline method was used, and this clearly led to significant savings to bridge owning authorities who effectively didn't need to carry out expensive strengthening work in those cases. However, the COBRAS program had a built-in library of failure mechanisms, but there's no way that that library could ever be exhaustive. I think there were 27 mechanisms on the slide I showed earlier. Even if you have 50 mechanisms or 100 mechanisms, there's always a chance that you will miss the critical mechanism. So there's always some concern that the critical Yieldline pattern hasn't been found. On the other hand, recourse to more complex tools such as non-linear finite elements is, as I mentioned earlier, expensive in terms of time and required operator expertise. So what we really would like to do is to systematically automate the Yieldline method to overcome the first problem, but without the drawback of the large amount of time required in the case of finite element analysis. And what we've been able to do recently is do just that. We've applied a technology called discontinuity layout optimization to rapidly and directly identify critical Yieldline patterns. And we've published that work in well-known science journal, Proceedings of the Royal Society A, just last year in 2014. We've demonstrated that the process of finding the critical Yieldline pattern with DiLo boils down to solving a simple linear optimization problem. How do we solve the problem using DiLo? Well, if we have a slab, first thing to do is to populate the slab with nodes. Typically, we would have a uniform distribution of nodes that we spread across the slab. We then connect those nodes together with potential discontinuities or yield lines in this case. And then we use optimization to find the critical subset of discontinuities that defines the yield line pattern. And you can see here the simple pattern that's been identified in this particular case. The more nodes we have, the more accurate the yield line pattern is likely to be, or the closer it is to the true pattern. How do we actually solve it mathematically speaking? Well, what we're basically doing is looking for a minimum energy solution where the internal energy is defined as the length times the moment capacity times the rotation at all yield lines, subject to two sets of constraints: compatibility at node constraints, which I'll talk about in the next slide, and according to the principle of virtual work, an imposed unit displacement constraint. So these are relatively simple linear constraints and a linear objective function as well. So Compatibility is considered using, at least in DiLo, at nodes. So if we zoom in on a node, for example, the node in the bottom left corner on the slide shown here, what we need to do is traverse around the node, and when we get back to the place we started from, then the net rotation should be 0. So if we sum all the rotations round that node, this should sum to 0. And the constraints in question, in this case, boil down to ensuring that we end up, if we resolve in the x direction all the rotations, those x direction rotations sum to 0, and also the y direction rotations also sum to 0. So it's actually analogous to resolving forces in a truss, which, if you're interested, is explored in a little bit more detail in a paper that appears in the October 2015 issue of the Structural Engineer, and actually which contains exactly the image I showed on the previous slide. So if you're interested, this paper explains it in a bit more detail. And although for copyright reasons we're not able to make available this paper on the website, if you drop us an email, we'll send you the paper, and also there is the preprint version of the paper that you can download on the website. So this gives this article gives a more accessible explanation of how we've been able to automate the Yieldline method than the Royal Society paper I mentioned earlier, which is more academic in nature. Okay, so that brings me towards the end of my section of the webinar. Just to sum up what I hope I've managed to get across. The Yieldline method is a powerful means of analysing the collapse limit state for concrete slabs, in particular concrete bridge slabs. Problem has been that there hasn't been an automated method, so instead people have had to resort to sort of lookup tables or doing it by hand. However, in the last year or two, we've been able to automate the method using DiLo, or discontinuity optimization, as its full term. This involves developing a relatively simple linear optimization problem, which is easy to solve, and that allows us to identify mechanisms of whatever form are critical in the particular case that you're interested in. So, for example, fan mechanisms can be identified very straightforwardly, and LimitState slab software, as you will be aware, can be downloaded from LimitState.com. There's a trial version that you can download. If you want to access all functionality of the full version, drop us an email and we can sort you out with a full version as well. Okay, so that's a sort of a brief introduction to the context and to the technology. I'm now going to pass you over to Tom, who's going to fire up the software and apply it to the analysis of the slabs found on bridge decks. So over to Tom now.
Thanks, Matthew. So what we're going to do today is just look at 3 different cases of bridge deck analysis. Firstly, just a simple slab with a single axle loading, and then getting progressively more complex. So secondly, an irregular shaped flat slab, again with some vehicle loading, and then lastly a beam and slab bridge deck example. What I'll do is just start up the software. So for the simple problem, what we're going to do is actually start from scratch with it. For those of you who aren't familiar with the software, it's sort of pretty straightforward. mainly driven from the toolbars around the edges, and also on the right hand side here the property editor, which you'll see shortly. Actually, if you click on anything within the interface, the properties of it will show up in the property editor, and you can then make changes accordingly. So what we'll do is start with an empty project in this case. As I said previously, we're just going to do a simple rectangular slab with a single axle loading on it. So the first screen is just general details. We don't need to worry too much about that. The second one is to set the grid settings within it, and all I'm doing here is just making sure that it auto calculates the extents of the grid so that when I'm drawing it will expand accordingly. So what I'm going to do is set up a bridge deck problem and put on a single axle load of 11.5 tons, and assume for now that the load is actually in the middle of the slab. We may want to look later at critical cases by moving that load about, and that's something that I'll demonstrate with one of the later examples. But first off, what we'll do is actually just draw the slab. So click on the blue icon here on the left, which is the rectangle draw, and we'll do it from 0, 0 up to a new point, which is 7.85. So 7.8 by 5 meter slab. You can see here that it's created in the middle. What we want to do now is actually add some boundary conditions to it, and what we can do here quite easily is just select with a rectangle around the upper and lower external boundaries, and as I mentioned previously in the property editor, anything you select on screen you can then change the properties of it within the property editor. So here the drop down's got external boundaries too, because they're the ones we've selected, and then you can see here in the support type at the moment it's free. If you click that drop down, you've got symmetry, fixed, simple and free, and what we want to do is just make that simple. So click on simple, click away, and you can see now that the boundaries have changed to the single hatch, which you would associate if you sort of used to Yieldline analysis with a simple support. We turn off the grid, so we've got a geometry, we also have the boundary conditions now. What we need to do is actually add the sort of mechanical properties to it as well, and that's done by creating what we call a slab definition. So on the left hand side of the screen here, if I right click in the slab definition explorer, you can see there's the option to create a new slab definition, and that brings up this window here. So I'm just going to call it my slab, and I'm going to make it a different color from the ones that already exist in there, just so that we can see that it's actually applied to the problem. And we'll make an orthotropic slab, and you can see here we've got first and second directions, and that's basically defining the angle at which the MP value works. So you can actually define orthotropic or isotropic slab properties as necessary. In our case, what we're going to do here is we're going to have an orthotropic, so the positive moment is 120 kilonewton meters per meter, and the negative is 10, so there's sort of minimal top reinforcement within the slab. And in the other direction, so at 90 degrees, we've got 15 for the positive value of MP and 2 for the negative. For the thickness, which would be used if you were taking into account the self-weight of the slab in the analysis, in this case we're not, but we'll put the value in anyway. We have 0.35 meters and a unit weight of 24 kilonewtons per meter cubed. We'll click OK, and you can see now that my slab as a slab definition has appeared in the Explorer to the left hand side, and what we can do is just click on it and drag it across to that central section, and once we let go we can see that the slab has now changed the same color as that. And if I click on that zone in the property editor on the right hand side, you can see here that the slab definition, my slab, has been applied to it. So we've got now a geometry, we've got boundary conditions, we have the mechanical properties of the slab. What we need to put onto it in order to be able to undertake our analysis is some loading, and that's done using these purple buttons at the top here. I'll click on the left hand one, which is the sort of load case manager dialog. The other three are sort of quick methods for applying point, line and area loading to it, but what we want to do in this case is just look at the load case manager. So click that. You can see that load cases are made up of a combination of partial safety factors and loading. So you can have as many as you want. So you can have sort of a number of load cases, and that's how we would actually move a vehicle around our slab. But in this case, we're just going to look at the single one in the center of it, as I mentioned previously. So what we want is some point loads. And if I select that, you can see there, what I actually want to do is add a new point load, because we have unit point load as a sort of built-in loading case, but what we want to do is actually apply our 11.5 ton axle load, which would be 56 kilonewtons per wheel. So I'm going to put it in there. Actually, no, I don't want to do that. I want to change that to 1, sorry, and add. There we are. I'm going to call it 56 kilonewton wheel load, 56 there, and we'll make it a variable type of load. So you can see there in the drop down we've got the choice of permanent, variable and accidental loading. Obviously for a live loading like a wheel load, then we choose the variable there for it. So click OK, and you can see now if we go back to the point loads in this our first load case, 56 kilonewton wheel load has appeared within the drop down dialog. So if I select that, to the right of it now there are a number of different options. So the action type is going to be unfavorable because it's pushing down on the slab. Adequacy is set to true, so all that's saying is that that is one of the loads that is factored up during the optimization in order to drive the collapse of the system. And then we've got the position, and what I want to do is actually stick it in the middle of the slab, so I know what the coordinates are for that. So if we put it at 4.8 and 2.5, and what we then want is another wheel next to it. So again, set it to unfavorable, adequacy true, and the coordinates for that are going to 3.0, 2.5. So it's just either side of the center line of the slab. Then what we would normally do after that is also apply some partial safety factors. You can see here at the top it's set to unity, but you can also create a new partial safety factor set just by clicking on that option in the drop down, and you can see here that you can vary the safety factors on the permanent, variable and accidental loading. We're just going to keep it as unity for the moment, but obviously according to whichever code of practice you'd be looking at the time, you can set your partial safety factors accordingly. So we've got two loads, one at 4.8, 2.5, one at 3.0, 2.5. If I click OK, and then the green button at the top here that says show loads, you can see that there are 2 point loads now in the center of the slab. And that's basically gone through and set up the whole problem. So we've drawn a geometry, we've applied the boundary conditions, we've put some material properties into it, and also applied some loading. So now all it remains for me to do is to solve. So if you click the green solve icon at the top there, you can see that the software goes through a number of different potential failure mechanisms and ends up here with an adequacy factor of 4.4 and this sort of expanded fan type failure mechanism, which actually, if I bring up the slideshow from previously, actually bears quite a resemblance to this interior horizontal wedge that Matthew was explaining about the sort of Cobra's program earlier. It's a similar failure mechanism to that, so that's that. And you can see here just a few things to note. We've solved it on a medium nodal density, so that's giving it 500 nodes within this system. You can actually, if I unlock, change that setting so the more accurate, the more sort of detailed you want the analysis to be. You can up the number of nodes that are actually in the problem. Obviously, it will take slightly longer to solve, but not that long. So if I just solve it again, The other thing is that if you go to analysis and then click on report, you'll see that you get the option to include a number of sections in your report, so a summary about the program, the geometry of the problem, the materials, partial factors, locators, etc. Click OK, and you can see you've got a tabulated report here that gives you all of the pertinent information about that problem, and you can use that to do what you want with. So we've gone through, we've done a sort of very simple problem really, rectangular slab with a single load case on it. The next thing I'm going to do is I will bring up the slide again. Is an irregular shaped flat slab with some vehicle loading. So you can see on here, it's actually based on the real case of a slab that was initially on the verge of a road, but during construction they covered over it and actually ended up extending the carriageway over the top of it, so they needed to actually look at the capacity of it to see whether this repurposing was sufficient to take the loading of larger vehicles over the top of it. So you can see we've got this irregular shape here with load support on 3 sides and a free edge on the right here, and then a vehicle loading which equates to 82 kilonewtons per wheel. So we're just going to go through that and set it up. Also, you can see I forgot to mention that there's a pressure load of 2.62 kilonewtons per meter squared over the top of it as well, and that's from the extra road surfacing that's gone over the top of it. Obviously, once they've put it into the middle of the carriageway, there's extra tarmac adam that's going to be over the top of it. So we need to take that into account also. So if I just start a new project, don't want to save the current one. Again, we'll just start with an empty project. So we need to draw the slab, and instead of using the rectangle, what we'll do is just use this polygon, and we can add some points. So we want 0.7850 to 1.6872, sorry. Start again. 0.7850 not 1.672 to 6.207 4.431 and then 0.5 doesn't seem to have actually solved. What I can actually do is I'll just open it. I'll open it, there we go. So we can see here that that's the shape of the slab, and what we can do then is actually add our boundary conditions. So you can see around the edges here we've applied simple support. So if I click on those, you can see external boundaries, and the support type is simple. On this right hand side here, click on that, the support type is free. And then we need to generate some slab mechanical properties, and if we click on there, you can see we've already predefined one called slab, where the first direction has a positive MP value of 90, and also in the second direction as well. The thickness is 0.31 meters, and again the unit weight 24. And then all we do to actually put the material onto the slab is to drag and drop it. In this case, it's going to say it's already present in this solid because I opened the file, but it's as simple as that. So the next thing to look at is the loading. So in this case, what we're wanting to do is actually traverse a vehicle across that slab rather than just have the one load case as we saw in the previous example. So if I open the loading dialog, you can see actually already this is all set up for us. We've got at the top here a pressure load, which is called superimposed, and the adequacy is true on that, and the position is on S1, which basically is the only solid in the problem. So if I just click change, you can see there, select it S1, and OK. What we also want is a number of point loads to represent the vehicle wheel loading as well. So what we've done here is at the bottom in the point load section is defined an 82 kilonewton wheel point load, set the action type to unfavorable, and then applied that at the right spacing to give the 4 wheel loads in the right position. And we're starting it off on the left hand side of the slab, and we're going to move the vehicle towards the right. The thing we can do there is actually copy that load case across to a number of load cases, but actually move the position of the point loads in each case across the slab. So you can see here we've already done that. So if I click the different tabs, you can see the values here of the point load positions are moving. In a second we can see that actually in the user interface. So we've set all that up and copied the load case across. So we've got this moving vehicle. If I just click OK, what I can do is turn on the display of the point loads, and you can see here at the bottom there's a number of tabs for the different load cases, and if I click on each one you can see that the vehicle is moving across. So all I need to do now is just solve. First off, if we go to Tools and Preferences, what we need to do is make sure that the viewpoint here in the general settings is set to bridge. So basically that means that the slab will stay central in the viewpoint and the vehicle will move across rather than it recentering each time. And then I click Solve, and you can see the software goes through each different load case and works out what the critical layout of Yieldlines is for each of those. And as it's running through, you can already see that the failure patterns that it's finding are quite different for different load cases depending on which wheel loads are actually on the slab at the particular time. But now it's finished, it's found that the 6th of our load cases here is the critical one, and that the adequacy factor associated with that is 1.43. If you're interested in the other load cases and the associated failure mechanisms for those, you can go through, and on each of the different tabs you can see exactly what the failure mechanism is for that. But for this one we can see that it's basically the free edge of the slab is falling away, and if I click this button here, what it will do is actually just animate the failure mechanism for us. So I'll just take it back, we can run it through so you can see there just exactly how it fails. And this is quite a simple problem, so the animation is doing exactly what we'd expect, but it comes into its own more when you're looking at quite complex Yieldline patterns. It proves to be a very useful way of actually visualizing what is happening at the collapse point for the slab. So we've found out with this case that we've got an adequacy factor of 1.43. If we just go back and look, so for our partial factor safety set that we have applied to it and these loaded conditions, we've got an adequacy factor of 1.43, which suggests that the slab is okay in this case. Although the suggestion from the critical failure pattern is that we may want to investigate more load positions towards the free edge, as the adequacy factor is actually reducing quite quickly towards this point. But that's something that would also be quite simple to do. So we've had a look at a very simple rectangular slab. We've also had a look at a slightly more complex slab in this case. The third problem that I'm going to look at very quickly is just an example of a beam and slab bridge deck, and this is actually based on the example in Jackson's thesis from 2010, which is in turn based on some work by Hazel, who was testing a scale bridge deck model. It's a system of simply supported longitudinal beams which are separated by a thinner slab deck. The slab's quite lightly reinforced, whereas the beams have more substantial reinforcement on them, and you'll see that in the model that we create shortly. Obviously they'll have different MP values, and we're going to look at the case here where we have two loads over the center of the left hand two beams. So in the middle there, I don't know if you can see, there are two squares, and they correspond to the points of these patch loads, and the load factor of the upper bound, which was found in Jackson's thesis, was 62. We unfortunately don't know exactly the material properties that were used there. We've got a good guess, so we're going to try and see what our software will come up with for that. So if I open SLAB again, we'll go for a new file. In this case, what we can do, because the geometry is slightly more involved, we're going to import the geometry as a DXF file, and what will happen is that the software will then interpret any closed loops within that DXF file as being the outsides of solid domain. So if I open this, you'll see we've got a DXF import dialog. It's asking us which layers we want to import. If we import all of them, we then have the geometry already set up for us, and you can see each of the different zones is selectable. So if you've got a particularly complex layout, like some of the building layouts that Matthew had shown in the presentation previously, something like that would be very easy to just set up as a DXF and import in, rather than drawing it within the program itself. So we've got a geometry, we've got the two squares where the patch loading is going. What we need to be doing is, as before, adding support conditions. So for the top and the bottom, on the external boundaries, just set the support type to be simple. We just need to then add mechanical properties for both the beam and for the slab sections. So we'll make a new slab definition. We will call this slab, and make this a nice pleasant yellow color. And for this one, for the positive MP, we'll have 5 kilonewton meters per meter, and for the negative 3, and then a thickness of 0.044, again unit weight of 24. And in the second direction, we'll have similar hogging and sagging material properties. So we've got the slab. The next thing to do is to make the beam. So obviously this is quite a lot stronger, and that's reflected in the MP values. So we're going to have 150 and 120 and 500 and 300 in the second direction. Thickness is slightly larger, so 0.204 to reflect the deeper beam section, and the unit weight again 24. So we've seen previously how we can drag and drop our material properties. The other method of actually assigning material properties to multiple zones at once is to select them, and then in the property editor on the right hand side, we can just click here and choose that material from the list of checkboxes and apply it to multiple areas at once, rather than selecting them each individually with the drag and drop method. So we've got geometry, we've got the boundary conditions, we've got the slab definitions applied, and what we need to do then is apply some point loading to the centers of these areas here. So what we're going to do is apply just 1 kilonewton point loads to the center of these left-hand beams. So add unit point, and I know the coordinates of the center of those, so 0.05, and then another unit point load at 0.41. Click OK. You can see again the adequacy is set to true for those, so they're the values that are going to get multiplied up when we're looking for a solution. If I click on the show loads, you can see here the two pink dots that signify that the point loads have been applied in those positions. And in this case, because it's a relatively simple single load case problem, what we can do is just set the nodal density to be very fine rather than the medium that it sets by default, and click solve. And you see as it's running through, it's coming up with failure in this second section of slab with a straight line. The adequacy factor is 54, which if we go back and compare to here where we had 62, it's suggesting that it's slightly lower. Obviously, like I say, we don't know what the material properties are for definite that were actually used in the original problem, but this is a good guess at them. Also, we can see that the failure mechanism that was obtained in Jackson's thesis looks very similar to the one that we've obtained, but ours is very much more complex, just showing exactly how powerful the analysis method is. So that's a beam and slab example problem. One of the things you might want to do in a case like this is actually traverse your load across a bridge. We do have an animation, if you bear with me, of that. So you can see here a similar problem, just moving a load, in this case diagonally, across a beam and slab problem, and you can see the different types of failure pattern that may occur. So either failure in one or two or multiple slab sections, and this one actually quite interesting where the vehicle is in the center of the problem. You get sort of radial yield line mechanisms as well as the sort of failure within the beam section, within the slab section, sorry. So we're coming towards the end of the webinar now. There's just time to see if we have any questions. If you do have one, then please just use the question functionality that is in the web interface, and we'll try and get through to you. So I did have one question about whether we can model columns. I guess it's something that you will have seen maybe on one of the previous slides, but what I can do is just show you very quickly on this exactly what we could do to model a column. So if I just turn on the grid, all I want to do is just draw a square and then delete the material from the inside of it, select all the boundaries and just set them to be simple or fixed depending on the properties of the column, obviously, and the connection to the slab, and then we can just solve it again. I've no idea what that's going to do to the result, but we'll find out shortly. So you can see here actually that it's forced the failure mechanism to the first slab section on the left there, whereas previously it was in the second section. The addition of that column has actually made it stronger in that area and has forced the failure mechanism away from it. You can see also the solution here is 75.5 compared to being, I think it was 54 in the previous example. So just adding that column there has made it quite a bit stronger. Yep, I just had question, could I have a copy of the yield line method for concrete slabs? Yes, certainly. What we can do is we can make that available to you via email. There's a version I think Matthew mentioned on the website, like a preprint version that you should be able to get, but we'll also do that. Also, it's probably worth mentioning that a copy of this webinar will also be available shortly afterwards for people to also watch and download. All right, I've had another question: could a ground spring distributed boundary condition be modelled? If I understand that right, then what we're thinking about is actually an upwards pressure load from beneath. So all we'd need to do there is go into it and actually within the pressure loads here, just select that and have it moving upwards rather than downwards, and you should be able to do that. I think actually that's brought us to the end, so I'll just round up now. So firstly, thanks everyone for actually taking the time to join us today. As I mentioned, the webinar will be available afterwards on our website as a download link, which actually take you to our YouTube channel, which is youtube.com/LimitState software, where you can see a recording of this and webinars for all of our software, including more for LimitState SLAB and also LimitState Ring and LimitState Geo. For people who are current users of the software, we do hope you learn something a bit new about the software, and if you've got any questions, obviously please do get in contact with us via telephone or info@limitstate.com. We'll be more than happy to help you. People who aren't current users of the software, we will be in touch just over the next few days to get some feedback and find out if you have any further questions and whether you find the software might be useful to you. Everyone might also be interested to know that we got another webinar coming up later this year, and also some for 2016, so please do look out for the event notifications that will be sent out by email and posted on our website, which is www.limitState.com/events. So again, thank you for taking the time to join us, and hope to see you all again for one of our future sessions. Goodbye.